Welcome to the deep dive. Today, we're jumping into something absolutely fundamental, something that fuels pretty much every living thing, fats and oils.
Right, and it's a topic that often gets, well, a bit confused. We talk about fats and oils in the kitchen, almost like they're the same thing,
Yeah, you kind of use them interchangeably.
but scientifically,
Yeah.
and definitely biologically, the differences really matter. So our mission today is pretty clear.
What are we diving into?
We're diving into insights from this specialized guide. It focuses on controlling what they call the three highs.
Ah, the big ones. High blood pressure, high blood sugar, and high blood lipids.
Exactly. And we want to cut through the usual confusion, understand what a lipid actually is, why our bodies rely on them, but also crucially, why having too much is a serious health issue.
That's the plan. And I think the best place to start is with that really basic question that trips people up. What's the real difference between a fat and an oil? Is it just like animal versus plant?
Well, the first distinction is actually quite straightforward. It's physical.
Physical, how so?
It really just comes down to their state, what they look like at room temperature.
Okay, so simple as that. If you can spread it, maybe like butter or lard, it's a fat because it's solid or, well, semi-solid.
Precisely. Butter, lard, duck fat, those are fats. And if you can pour it,
Then it's an oil, like canola oil, olive oil, vegetable oil. They're liquid at room temp.
yep. The science behind that difference is simply their melting point. If it stays liquid below about, say, 68 degrees Fahrenheit or 20 Celsius, we class it as an oil.
Okay, that makes sense. And, there used to be that kind of handy rule of thumb, right? That fats usually came from animals.
And oils usually came from plants. That often holds true. It aligns a lot of the time.
But I sense a but coming.
Well, yeah. Like with a lot of things in science, relying only on that animal versus plant idea is where things get messy.
Ah, the exceptions.
Exactly. The physical state, which is actually driven by the chemical structure, that's the real defining factor. That's the boss here.
Okay, let's unpack these exceptions then, because I think this is where it gets really interesting for you listening. You might think, okay, plant stuff equals liquid oil, but coconut oil.
Perfect example. Sits there on the shelf looking pretty solid, doesn't it?
It really does.
So coconut oil and palm kernel oil, too, they come from plants, absolutely. But scientifically, they are classified as fats.
Why, though? What's making a plant product behave like butter or lard?
Okay, so it boils down to their chemical makeup, specifically something called saturation.
Saturation. Heard that term a lot.
Right. When we talk fat chemistry, we're looking at these long chains of carbon atoms. Saturated just means that chain is holding on to every single hydrogen atom it possibly can. It's completely full.
Fully loaded with hydrogen. And what does that do to the shape?
It makes the chains very straight, very uniform. Think of them like stiff little rods.
Okay, straight rods.
And because they're straight, they can pack together really, really tightly, like stacking planks of wood perfectly.
Ah, so they pack densely?
Exactly. And that dense packing means you need more energy, more heat to break them apart and make them liquid. So they have a higher melting point. They stay solid at room temperature.
So that's why coconut oil, even though it's from a plant, is a fat. High saturation, tight packing, solid state. Got it.
Precisely. It overrides the plant origin rule. It's the chemistry dictating the physical form.
And we see the flip side with animal products too, don't we?
We do. Think about fish oils.
Right. Definitely from an animal source.
But they're liquid, right? You pour fish oil. So they're classified as oils.
And following the logic, that must be because they're not saturated.
Exactly. Fish oils are high in polyunsaturated fats. Poly, meaning many double bonds in those carbon chains. These double bonds create kinks or bends in the chain.
So they're not straight rods anymore, more like bendy straws?
Sort of, yeah. They can't pack together tightly because of those bends. They slide past each other easily.
Keeping them liquid even at cooler temperatures, so they're oils.
That's it. So the real aha moment here for you is realizing that the physical state, solid or liquid, driven by that saturation level and melting point, that's the key difference. Not just whether it came from a cow or a cornfield.
Okay, that distinction is much clearer now. Solid fat, liquid oil, based on chemistry.
And once we grasp that, we can move from just thinking about cooking to understanding what's happening inside our bodies. Because whether it's solid butter or liquid olive oil,
Chemically, they're related.
Very much so.
Mm.
Biologically and chemically, they belong to the same fundamental class of molecules.
Which brings us into biochemistry, right? What are they called chemically?
They are both types of triglycerides. That's the specific chemical name we need to focus on.
Triglycerides. Okay.
And triglycerides themselves are part of a much broader category called lipids.
Lipids. So lipids is the big umbrella term.
Think of lipids as basically anything fatty, oily, or waxy in nature
Mm.
that, crucially, doesn't mix well with water. Triglycerides are the main players, the real workhorses, within that lipid family, especially for energy.
And what makes up a triglyceride, like structurally?
It's actually quite elegant. It's got a backbone molecule called glycerol. And attached to that backbone are 3 fatty acid chains.
3 chains. So that's the tri part.
Exactly. Try it for 3 fatty acids connected to the glyceride, which refers to the glycerol backbone. 3 chains hanging off a simple structure.
Got it. So why are these triglycerides so important inside us? What are they actually doing?
Their number one job, energy storage. They are the body's ultimate way to pack away energy efficiently.
Like little fuel tanks.
Perfect analogy. When we eat more calories than we need immediately, whether those calories come from carbs, proteins, or fats themselves, the body converts the excess into triglycerides.
And where do they go?
They get stored primarily in our adipose tissue, our fat cells.
Right. Our source material had that other great analogy too, didn't it? Calling them floating batteries or maybe energy bars.
Yeah, that captures it well. It's like archiving potential energy ready for when we need it. It's a brilliant survival mechanism, really.
Absolutely. But it's not just about locking energy away, is it? We use it too.
Oh, constantly. It's a dynamic process. We store fat, yes, but we're also designed to access and release it very effectively.
When would that happen?
Well, if you skip a meal, for instance, or more significantly, when you're physically active and your muscles need more fuel, the body doesn't just run out, it taps into those reserves.
It mobilizes the stored triglycerides. How does that actually work? Does it just like squeeze the fat cells?
Not quite that crude. It's a regulated hormonal process. Specific enzymes get activated inside the fat cells.
Okay, enzymes.
And these enzymes break the stored triglycerides back down into their components, the glycerol backbone, and those 3 fatty acid chains.
Ah, they take them apart again.
Right. And then those fatty acids, which are the actual fuel molecules, are released directly from the fat cell into the bloodstream.
So they travel through our blood.
Yep. They get picked up by carrier proteins, like albumin, and transported to tissues that need energy muscles, the liver, the heart, where they get burned for fuel. It's literally your backup energy supply on the move.
Okay, so they're essential. They store energy, we release it when needed. It's a constant healthy cycle. So why? Why does that health guide we mentioned, the one focused on high-risk factors, flag high lipids, as something dangerous we need to control?
That's the crucial question. Storage itself isn't the problem. It's excess circulating in the system.
So high lipids specifically means too many triglycerides floating around in the blood.
Exactly. The medical term is hypertriglyceridemia. Too many triglycerides circulating.
But if we're good at using them, why would they build up like that?
Well, it often comes down to a chronic surplus of calories, especially from diets very high in refined carbohydrates and sugars.
Carbs and sugar, not just fat.
Correct. The liver is very efficient at converting excess sugars and starches into triglycerides. So if you're constantly overloading on those,
The liver just keeps pumping out triglycerides.
it does. It packages them up into these little transport particles, mainly things called VLDLs, very low-density lipoproteins.
Okay, VLDLs, like delivery trucks for the fat.
That's a great way to think about it.
Yeah.
And the problem starts when there are just too many of these trucks, overloaded with triglycerides, hitting the bloodstream all the time.
Right. The system gets overwhelmed.
It does. Our source material uses that really vivid analogy. An oversaturated bloodstream is like a tiny road, just flooded with way too much traffic.
Too many delivery trucks, too much cargo, causing gridlock on the circulatory highway.
Precisely. Normally, your muscles and tissues would efficiently pull the fat off these VLDL trucks as they pass by. But when the volume is constantly high, the system can't keep up.
And that traffic jam isn't just inconvenient, is it? It's actually harmful.
It is. That persistent excess of triglycerides and the VLDL particles carrying them contributes directly to inflammation in the blood vessel walls. It can start to damage the lining.
And when that happens over time, especially in important arteries, near the heart or brain,
That's when you increase the risk of serious problems like atherosclerosis. That's the hardening and narrowing of the arteries. Plaque can build up.
so the very thing designed to be our backup fuel.
Becomes a major liability when there's just too much of it constantly circulating. It flips from being an essential energy source
Hmm.
to a significant risk factor for blockages, heart attacks, stroke.
Wow. That really connects the kitchen science to serious health outcomes. Okay, let's quickly recap the key points for you listening.
Good idea.
We figured out that fat versus oil isn't always about animal versus plant. The real difference is physical state solid or liquid at room temp.
Which is determined by the chemical structure, specifically saturation. Higher saturation means straighter chains, tighter packing, higher melting point, usually solid fat.
Lower saturation or unsaturation means bent chains, looser packing, lower melting point, usually liquid oil.
And chemically, both fats and oils are triglycerides, which are a type of lipid.
Right. And in the body, triglycerides are essential energy storage tanks, are floating batteries.
Absolutely. Stored in fat cells, mobilized by enzymes, and released as fatty acids into the blood to fuel activity. A vital process.
And this is the critical link to health chronic excess of these triglycerides circulating in the blood, the high lipids, creates that dangerous metabolic traffic jam.
Turning our essential fuel source into a potential cardiovascular risk due to oversaturation and potential blockage.
Which really leads to a powerful follow-up question for you to think about. We know triglycerides are stored energy released for activity.
Right. Diet provides the input, activity drives the output, the utilization.
So what other factors decide how well those floating batteries actually get used? Think about things like insulin sensitivity, maybe the type or intensity of physical activity. What determines if that energy gets efficiently burned or if it just stays stuck, contributing to that traffic jam in the bloodstream?
That's something really worth considering. How effectively are your energy stores being mobilized and used?
Definitely food for thought. Thanks for joining us for this deep dive.